My dear students, let me welcome you all to a new edition of physics. In this edition, we'll learn about transistors, types of transistor, but we'll focus on bipolar junction transistors. Also, I'll explain the function of transistors in electronic circuits, types of electronic circuits, and logic gates. So let's get started. Transistors. Types of transistor. As a matter of fact, there are many types of transistor, but we'll focus on the bipolar junction transistors. Bipolar junction transistors, yes, are abbreviated by BJT. So once again, we'll focus on the bipolar junction transistors. First of all, what is a bipolar junction transistor? Well, it is made of three layers, three slices of semiconductors. A bipolar junction transistor is made of three layers of extrinsic semiconductors. Extrinsic semiconductors means, yes, they contain impurities. The layers are called the emitter, the base, and the collector. Okay, so we've got three layers, emitter, and it is denoted by capital E, base, denoted by capital B, and collector, denoted by capital C. Examples for such transistors. Yes, the first type is NPN transistor. It is a slice of P-type between two pieces of N-type semiconductor. Once again, it is a slice of P-type between two pieces of N-type semiconductors. It is shown right now on the screen. So the base is made of P-type semiconductor, which is different from the type of the other two pieces. Emitter and collector are made of N-type. Okay, what about the symbol, electronic symbol? Yes, it is given a circle, and your attention to the direction of the arrow on the figure. Okay, this is the first type of the transistors, bipolar junction transistor. Second type is PNP transistor, and it is a slice of N-type material between two pieces of P-type semiconductors. N-type between two pieces of P-type. And what about its sample? Okay, note the direction of the arrow is reversed. Okay. We've got something very important here to mention. The arrow of the emitter, arrow drawn on the emitter, shows the direction of the conventional current. And of course, let me remind you with conventional current. It is the, yes, direction of motion of positive charges. So direction of the arrow on the emitter is the direction of the conventional current, positive charges. The base of the transistor is deliberately made very thin and is lightly doped. Let me say it again. Base is very thin and lightly doped. The rule here, emitter current equals base current plus collector current. You'll note that emitter current is equal to base current plus the collector current. And now talking about the action of the transistor. your attention, please. Okay, talking about the action of the transistor. As a matter of fact, transistors act as fast switches and as amplifiers. So they act as switches and amplifiers. In front of you, we've got NPN transistor, and it is connected to a potential difference of 6 volts. As you see, a potential difference of 6 volts is applied across NPN transistor. And you can see that the base is not connected, it is unconnected. Okay, so no current passes in this particular case when the base is not connected. Okay, no current passes through the transistor. Why? Because the base collector is reverse biased. So in front of you, we don't have any current when the base is not connected, because in this case, base collector will be reverse biased. Okay, but when the base is connected to a positive potential of about 0.6 or 0.7 volt, okay, electrons will flow from the N-type emitter across the junction into the P-type base. So your attention, please. The base in this case, in the NPN type, should be connected to a positive potential, at least 0.6 or 0.7 volt. In this case, electrons will flow from the emitter, okay, to the collector. But not all the electrons that cross the base reach the collector. This is very important piece of information. Not all the electrons that cross the base reach the collector, because some of the electrons, some of them, combine with some holes. You remember, base is made of p-type, so it contains holes. Some electrons from the emitter recombine with the holes found in the base. Okay. In this case, yes, the junction between emitter and base is forward biased. And let me remind you something. Emitter current is always, yes, equal to base current plus collector current. Thus, if IE is the emitter current, then alpha E is the fraction, percentage of the emitter current that reaches the collector. As I said, not all the electrons of the emitter reach the collector. It is portion, just portion of it. Okay, alpha E is the fraction of the emitter current that reaches the collector. Emitter current equals base current plus collector current. So what about the base current? It's all easy. It is I emitter minus I collector. It is I emitter minus, okay, I collector equals alpha E times the emitter current. 90% of the emitter current will reach the collector. Okay, so collector current equals alpha E I emitter. Of course, I emitter will be taken as a common factor, so base current equals IE between two brackets 1 minus alpha E. So we managed to obtain the base current in terms of alpha E and current of the emitter. If we regard IB as the input current, base current is the input current, collector current is the output current. Okay, once again, if we regard I base as the input, I collector as the output, okay, a transistor acts as, first of all, a switch in which base current turns on and controls collector current. So first function of the transistor, it acts as a switch. An emitter current controls the collector current. That's to say, if base current equals 0, then collector current will be 0. Once again, base current controls the collector current. If voltage across base and emitter is equal to 0.6 volt, yes, base current starts to flow. Thereafter, collector current increases when I base increases. Also, a transistor can act as a current amplifier. The question is how? IC collector current is much greater than IB base current. Let me remind you with something. IC is the output current. Base current is the input current. Okay? So since IC is much greater than IB, and a small change in the base current causes remarkable change in the collector current, so it acts as an amplifier. And we've got current gain. Current gain is denoted by beta E, which is the ratio between collector current and base current. Collector current equals alpha E, I emitter. Base current, we've managed to obtain that base current is equal to 1 minus alpha E between two brackets times emitter current, and of course emitter current will be crossed out. So current gain equals alpha E over 1 minus alpha E, and don't never forget it is always the ratio between collector current to base current, or a change in the collector current to the change in the base current. And now we'll talk in details about the function of the transistor as a switch. In front of you, we've got a circuit, okay? And there is something very important. You should focus on the base, because the base controls the device. Okay? Is it connected to a positive voltage? If it is connected to a suitable positive voltage, a current passes through the base and a current flows through the collector. In front of you, okay, the base is connected to a positive suitable potential. VCC is the total voltage, and of course it is equal to the sum of VCE plus ICRC. ICRC is the voltage across the collector. VCE is the, yes, output voltage. Okay. Once again, the base is connected to the positive terminal. In this case, the output voltage is equal to 0. The question is why? Current passes through the base. Okay. A large current passes through the collector, and this means ICRC very huge. And of course, since the sum of VCE plus ICRC is equal to a constant, which is VCC, so when ICRC increases, VCE decreases. So in this particular case, Vout is equal to 0. Okay, VCC in this case is equal to ICRC. But now, what if the base is connected to the negative terminal? Okay, no current passes through the base, and of course, this controls the collector current. No current passes through the collector. Once again, VCC is equal to VCE plus ICRC. In this case, ICRC is equal to 0. Okay, so VCC is equal to VCE. The question is why? Once again, base current in this case is 0. When the base is connected to a negative potential, no current passes through it, and of course, no current passes through the collector. So ICRC equals 0. IC equals 0. The product will be 0. So it turns out that VCC equals VCE. That is to say, when the base voltage is too low or negative, the transistor is off. And the collector current is very small, so the output voltage on the collector emitter is high. And now talking about types of electronics. As a matter of fact, we've got two types, digital and analog. We'll start with the digital electronics. As I said, there are two types of electronics: analog electronics. And what about analog electronics? In analog electronics, the information about a certain natural quantity, such as sound, image, or heat. What about the information concerning these quantities? Yeah, they are converted into changing current or voltage. So, in analog electronics, the information about a certain natural quantity, sound, image, or heat, is completely converted into an electric signal in the form of a varying current or voltage. Okay, this was about analog electronics. And what about digital electronics? In this particular case, the information about a natural quantity is coded into a digital form. So, information is converted or coded into a digital form. Codes used in digital systems are, first of all, decimal code and the binary code. Decimal means it consists of 10 digits. Binary means it consists of 2 digits. So once again, codes used in digital systems are decimal and binary. Examples for analog electronics. So back to the first type. Examples for analog electronics. Okay, the way the image, we call image is video, okay? The way the image and the sound is transmitted from a transmitter, and the way they are received, the way the video and audio are received at a receiver to operate a TV set, okay? This is an example of analog, yes, electronics. But examples for digital electronics, your calculator. Okay, your calculator is a digital form. The processor in your calculator, which processes the data, works with digital information. Processor works with the digital information. Also, your computer is an example for digital electronics. As a matter of fact, a computer can only execute instructions by counting with just 2 numbers at a time. Let me say it again. It can only execute operations by counting just two numbers at a time. Okay. The numbers, of course, are, yes, 0 and 1. This is the binary system. And now we'll try to convert from decimal into binary. So conversion of decimal numbers to binary ones. For example, 43 is a decimal number. Okay, we want to encode it into, yes, binary codes to take the form of 0 and 1. Okay, we'll learn how to do it. First of all, 43 is divided by 2. It will give 21. Remainder here is 1. Okay? And we'll do the same with the 21. When divided by 2, it will give 20. 2 times 21 by 2, it will give, yes, 10. 2 times 10 is 20. 20 minus 21 is, yes, we've got 1. Remainder. 10 divided by 2, it will give 5. 2 times 5 is equal to 10. So we don't have anything left. Remainder equals 0. And 5, when multiplied by 2, it will give 2. 2 times 2 is equal to 4. 4 minus, or 5 minus 4, we've got a remainder here, which is 1. 2 divided 2, yes, it will be 1. Okay, remainder is 0. And 1 over 2, yes, we don't find any 2's in figure 1, so it will give 0. Remainder is 1. And your attention, please, to observe how we will write the, yes, number. It will be 1, 0, 1, 0, 1, 1 to the base of 2. Okay. We've got something here to mention. If we want to mention the base in which a number is written, we write the base as a subscript next to the number. Let me say it again. If we want to mention the base in which a number is written, we write the base as a subscript next to the number. For example, between two brackets, 356 to the base of 10 means it is decimal. Okay. 1011 to the base of 2. Okay. Or 1011 between two brackets, and we've got 2. This means that 1011 to the base of 2. Okay, so it is a binary number. And now talking about advantages of digital systems. Yes, digital systems are very easy to design and build. Inputs and outputs are easy to join because they recognize the same voltage as logic levels 0 or 1. So once again, inputs and outputs are easy to join because they recognize the same voltage as logic levels 0 or 1. Information is very precise, talking about advantages of digital systems. So, information is very precise. Information can be stored very easily. Digital circuits can be fully integrated. This is very important. Digital circuits can be fully integrated, okay, to work as just one device. Digital circuits can think faster, and we've got very important to give reason here. Digital transmission is preferred to analog one. digital transmission is preferred to analog one. Digital coded pulses are very simple to transmit. So the answer, digital coded pulses are very simple to transmit. They are either a 1 or a 0, high voltage or low voltage. Unlike analog signals, which can only be amplified along with the noises. Digital pulses can be very easily regenerated to their original form with no unwanted noise and no information is lost. In a digital system, this is very important. It is only necessary to detect the presence or absence, 1 or 0, of a pulse. So it is only necessary to detect the presence or absence of a pulse. The shape of the pulse does not matter at all. The information does not lie in the absolute value of the signal, but in the code 0 or 1. That's to say, it doesn't matter whether the pulse is contaminated with noise or not. Okay, what really matters is the state itself, state 0 or state 1. Okay. In this way, we've come to the end of this edition. Until we meet again, my best wishes.